We can start, I think. Job Thomas, sir.
Okay. Good evening, one and all. Indian Qcrete Institute, Kochi Center is always in the forefront in disseminating knowledge to the civil engineering community. The Kochi Center regularly conduct online as well as offline programs in every month to get in touch with the civil engineering people around the Kochi Center and around India. This is one among them. Today, we got an eminent speaker in the area of concrete technology, Dr. Saroj Mandal. He is the professor in civil engineering at Jadavpur University, and he is the vice president of ICA in the Eastern region. I welcome you, sir, for this program. This program is sponsored by Qcrete. I welcome Engineer Shirley Fernandez, Engineer V.R. Kaushika, who were instrumental in associating this webinar series with ICA Kochi Center. I welcome all Qcrete officials to this function. ICA executive members are keen in developing long-term relationship with the construction industry. I welcome the chairman of ICA Kochi Center, Dr. Anil Joseph, Dr. Elson John, Vice President, Engineer Shaiju S. Nair, Dr. Sunita Nair to this program. I welcome all the participants of this program. Without you, ICA cannot survive. Thank you very much.
Good evening. Myself, Kaushik from Qcrete Readymix India Private Limited. Just once again, welcome Dr. Saroj Mandal, who immediately accepted our invitation once we asked him to come and deliver the lecture. We are privileged and we are extremely thankful to you, Dr. Saroj Mandal, sir, for the gesture that you have shown towards us. We have been doing the webinar series from 2020, and today is our 58th webinar. I'm sure many of the students and concrete industry professionals have shown interest and are getting some benefit out of these webinars. We are also thankful to Kochi Center for supporting us, all the office members of Kochi Center, including Dr. Anil Joseph, Dr. Shaiju Nair, Job Thomas, Elson John, etc. Thank you. And I hope the audience today will enjoy Dr. Saroj Mandal's excellent lecture. And once again, we are thankful to you, Dr. Saroj Mandal, sir. We are privileged to have you today. Thank you. Introduction by, now it is introduction of speaker by Dr. Anil Joseph, sir.
Yeah, thank you, Kaushik sir. It's a pleasure for me to introduce one of the great personality in the field of concrete technology in the country, Dr. Saroj Mandal, and a very, very interesting topic, the bacterial concrete, an innovative material. So the technology is changing rapidly, and it's a very important aspect the younger generation should know. Let me take the pleasure of introducing Dr. Saroj Mandal, a good friend and a very eminent personality in the area of concrete in the country. Dr. Saroj Mandal is a professor and ex-head of the Department of Civil Engineering at Jadavpur University in Calcutta, India, which has produced some of the luminaries in the field of the engineering industry across the country. He is also currently the Vice President East of the Indian Concrete Institute. His research focuses on advanced concrete such as high performance concrete and bacterial concrete, both very interesting topics, and has been funded by various government and private agencies. He is a pioneer in the field of bacterial concrete and has been awarded Indian and most importantly US patents for his works. He has published 75 peer-reviewed papers in journals and proceedings and is a regular reviewer for several international journals. He has also performed consultancy projects for government and private organizations and is a member of various professional bodies such as Institution of Engineers, Indian Concrete Institute, International Center for Fiber Reinforced Concrete, Indian Society of Wind Engineering, and Indian Society for Technical Education. It's a great privilege for me to introduce a dynamic personality, Dr. Saroj Mandal, to this august audience, and look forward for hearing you the latest what is happening in the bacterial concrete. Over to you, sir.
Thank you, Dr. Joseph. Before I start, can you hear me?
Yeah, we can hear you. We can hear you, sir. Yeah.
Okay, thank you. Before going to start, I like to thank Indian Concrete Institute Kochi Center and the Qcrete who have arranged this webinar on a very important topic, bacterial concrete and innovative materials. And I also thank other dignitaries present in the panelists, Dr. Thomas, Dr. Joseph, Engineer Nair, and Engineer Koshika for inviting me in this webinar. So let us start the lecture now. And before I start, the topic is basically not exactly the civil engineering, it is the materials, and it is also you can say it is a interdisciplinary subject. So that's why I have in this research I have included my friend Professor Dr. B.D. Chattopadhyay, Department of Physics. He is a biophysics man and he has taken care of all this bacterial part actually, and I am taking care of the concrete part. So it is a joint venture between your two departments of Jadavpur University and also the research scholars of civil engineering and physics department also. Now, all we know that concrete is a very concrete is a composite material and it has a lot of pores within the concrete. And we always try to improve this porous structure of this concrete by different properties of this and to improve these different properties of this concrete by various means. So our basic aim to reduce this porosity is basically to make the concrete is a very high performance and the durability. So these are the two important parameters we have to choose to get a good concrete material, and for this we have to going on developing the different methods to improve these two important properties. We know that present day there is a lot of works is going on. High performance concrete, fiber reinforced concrete, high volume fly ash concrete, cell compacting concrete, almost all these are now in usable stage. Geopolymer concrete is also a very good material, sustainable material. This is also a lot of development has been taking place both in India and abroad. And lastly, I want to introduce this bacterial concrete, that is today's topic. We know that bacterial concrete is almost, it has started in the year of 2005. We have started our journey and then it is now 2023. So almost a lot of development has been takes place in India and all the other places. In short, we can know that bacteria, there is a different microorganisms are there these are in our environment. These are basically omnipresent and omnipotent. And there are different types of microorganisms like bacteria, cyanobacteria, algae, lichens, yeast, fungi, and mosses. And mostly we know that sometimes they're very good for our different food like your carbs, beer, breads like this. And these are useful for this. Now, other effect, they are also very much harmful for this. So basically, all these microorganisms we can divide into two different criteria. One is harmful effect, another is your beneficial effect. If we come to our normal digestive systems. We have some good bacteria which helps for digestions, and there are some bad bacteria which will create some problems, right? So we have to think of which is beneficial for the concrete and which is harmful for the concrete. We know that harmful effects are like some of the acidophilic bacteria, mostly in your swell lines. You are getting this kind of bacteria, and these are very much harmful, and they are corrode the swell lines. Whereas there are some beneficial effect. Also, there are some bacteria. Basically, these are selective microbial agents, and you have to find out from the environment which bacteria is effective for your concrete. That will be beneficial effect for the concrete. So basically, for this, we have started our journey, and we have developed, or we are finding out some microorganisms along with some nutrient, because if we do not provide any nutrient, it will not live within the system. So we have to give some foods, basically. Nutrient means food to make your microorganisms live in the systems. Now, what is bacterial concrete? In basic general terms, we can say we know the concrete is cement, aggregate. Aggregate means both fine and coarse aggregate, and the water, and along with some additives. But here what we are doing, we are adding some microorganisms. Which type of microorganisms? Which are beneficial for the concrete, and beneficial means that will improve some strength by whatever improvement in your matrix structures. I will discuss later on that. Now, how we can apply this? That is also very important terms. I have already discussed. It can be used as a admixtures, that is microorganisms plus nutrient as a liquid, which is most common. And for that, we have got an Indian patent. It can be also used as a dry powder, like your protein powder. Normally, we eat protein powder. Just like similar situations, we have developed some protein powder from that microorganisms deposits. And this can be also used in the form of a liquid by mixing with water. And for that, we have got an US patent. And there is also another challenge we're now facing, where it is on process, that is active and dormant microorganisms. This is an ongoing project. I will discuss later on that. Now, it can be also just like it can be also as admixtures, that is along with during a mixing stage, we can add it. It can be also as a self-healing agent. One of the advantage in these cases that normally when you're injecting any polymer materials, they have a very high viscosity. But as it is a very low viscosity, it can move very faster, and it can go to the very thin or very nano level pores within that. It can be also used as an external coating. Just by spraying, we can also use it. So let us divide my lecture into different parts. I think there are 4 parts. Part 1, that is the very basic, and for that we have got an Indian patent. We have in these sections, we have choose some bacteria which is compatible with the concrete. How we have chosen? Because we have to choose some prerequisites, like it should not give any health hazard, because we have to work with these and we have to use in this concrete. What are the foods needed to leave this bacteria? That is also important parameters. That is, it should not be too cost. pH of the concrete, because we know the concrete is a very alkaline resistant. So our bacteria or the microorganisms, when we add within the concrete, it should not die. Performance in the concrete, naturally, that is my aim. That is, it should give some performance either in terms of durability or in terms of strength, by whatever means. Then we have to think of the lifespan, how much time it will spend within this concrete system. So within this prerequisites, we have chosen some bacteria. In fact, there are different researchers have used different bacteria, just like your Ramakrishna Shuki's Bank, South Dakota School of Mines. In fact, they have started very early ages. They are using Bacillus pasteuria and Pseudomonas aeruginosa. Professor Heng from Delft University of Technology, Netherlands, they have used Bacillus cohini. Professor N.D. Bailey, Ghent University, Belgium, they have used Bacillus speraceus. And all this character of this bacteria within this system of concrete, that they produce a calcite precipitations. That is what is called your calcium carbonate. And these precipitations basically fill the pores within the concrete, and that's why they improve. There is an improvement in strength. But in our Jadavpur University, we have a special bacteria we have collected from hot spring in very near to Kolkata. Why you have chosen hot spring? As it is very known that concrete is a very hot, very initial stage. That's why we choose a hot spring bacteria. And we have also taken some common E. coli bacteria for comparisons, and also some marine bacteria. And also we have noted that in these two cases we don't get any improvement. And we have chosen 3 different types of bacteria at different temperature range: 42 degrees C, 65 degrees C, and 72 degrees C. And finally, we have achieved that 65 degrees C is the most, you can say the most critical, or you can say the most advantageous bacteria for our concrete. Now, this is the locations of your, it is in West Bengal, and this is the Bacterial. It is almost a tourist place now. Everybody go there for bath in this hot water. So one thing it can be sure that there should not be any health hazard for this. Now, what are the steps followed for after these collections? There is sample collections. We have to prepare the medium or nutrient, removal of the chlorides. That is, if there is any chloride presence, we have to remove, adjust the pH to 8, sterilize the medium by autoclaving. That is so that there should not be any other microorganisms are there. Made anaerobic by passing carbon dioxide. Why it is done, I will discuss later. Inoculations of bacteria from culture, and then it is incubations for growth. So basically, we after collecting this bacteria, we add some nutrient or medium to grow it in a incubation chamber. So we can grow from a 1 bacteria to 1,000 to lakhs of bacteria, sometimes crores of bacteria within a short time. Now, this is the bacterial colony in anaerobic Petri plate. From 42-degree temperature, you have seen same view of 3 different bacteria. 1A and 1B is for 42 degrees C, almost round shaped. 2A and 2B is actually it is a fiber shape. 3A and 3B is that is on 72 degrees C. It is also like a fiber shape. Now, what we have started after getting this, we have started adding within the concrete and the mortar both, and we have tried to measure what is the strength improvement or tensile strength at different ages, and we got a positive results. For that, we have used different 53 and OPC. Also, you use your Portland slag cement, Portland pozzolana. We have tried with Yanor sand, natural sand. This is a step-by-step procedure. First, you started with mortar, then you started for the concrete. And most important is you have used distilled water, and also naturally the microorganisms and the nutrient. Now, this is the mixer proportions. We have used cement is to sand 1:3, water cement ratio we have taken 0.4. For the concrete, we have used 1:1.5:3 is by weight. Water cement ratio has been taken 0.5. Now, most important part is the microorganisms, how we have measured. That is also important. That is, we have used difference at 10 to the power 4 to 10 to the power cells per ml of water. How it is measured? Suppose you know that there is a liquid, that is what you can say the your nutrient plus bacteria. We know somehow what is the cell concentration. That is, say 1 ml of water say contain 1 lakhs of microorganisms. Now we know how much water is used for a particular meter cube of concrete. So accordingly, I can pick up how much quantity of nutrient along with bacteria is to be taken out for the concrete. Now, after applications of these 3 isolated bacteria strain, that is your 42 degrees, 65 and 72 degree, we have in a different cell concentrations, that is 10 to the power 4 per ml of water use, 10 to the power 5 per ml of water use, 10 to the power 6 per ml of water use. These are basically the strength of the mortar, average mortar composite strength. And if you have seen that, with respect to the without any cell concentrations at the 3 days, or you can see the 42 degrees C and 72 degrees C, there is not so much improvement. But with a 65 degrees C temperature, we have get a lot of improvement In fact, at 10 to the power 5, we are getting 25% improvement in strength. Then we have, this is the same as your, in your, what is called your bar chart diagrams. Then we have started with other, what we have started that we have only added the nutrient, whether there is an improvement or not, right? Because we may think of that nutrient may affect on your concrete, but again, we have added some dead bacteria. That is, we have give a heat to the solutions, that is bacterial solution. That means all bacteria will be dead in that cases. Then we have also added E. coli bacteria on the cement mortar, and all these three cases we don't get any positive results. So it indicates that this bacteria at 72 degrees temperature has some beneficial effect to the concrete. Now we have again started with, after mortar, you started with concrete. And in the same manner, we have here we have started in a more elaborate study has been made, starting from 10 to the power 2 to 10 to the power 7, and 3 days, 7 days, 14 days, and 28 days. Here we have used only 72 degree temperature microorganisms. Now we have seen in these cases at 10 to the power 5, we are getting also improvement of strength 20 to 25% at different ages. This is what is we are getting your cell concentrations and your also we have tested the split cylinder strength. This is also we are getting similar result at 10 to the power 5 cells per ml. We are getting a very high value of split tensile strength. Now then we have started some microstructure study. One of the most important part is the mercury intrusion porosimetry. This gives the amount of pores and the total quantity of pores and the pore diameter, right? So we have studied that 0 cell, 10 to the power 7, 10 to the power 5, and 10 to the power 3. So this one is the black one is 0 cells, then it is 10 to the power 3, then it comes 10 to the power 7, and then come 10 to the power 5. So what we are getting in this scale, if you see in the x-axis, there is a pore diameter, and then in the y-axis, we are getting the cumulative volume. So as we are seeing that at 10 to the power 5 cell, that is at the lower curves, we are getting at any particular pore diameter, the total volume has been reduced, cumulative volume has been reduced, and also the pore diameter is also reduced. So it indicates there is some changes has been made in this concrete matrix or the cement matrix. Now, we also have tested the softivity, and at 10 to the power 5 cells per ml, we are getting basically the less softivity as per these results. That is, it has been taken as per ASTM standard for this. So it indicates there is again some durability issues. We are getting much more durable structures if we use this bacterial concrete. And with this, we have applied a patent. I got a patent on this. Now, results are more encouraging for what we call for PPC cement and PSC cement. Due to the shortage of time, I am not going to details of this. Now, come to the second part. Second part, after getting all these positive results for 72 degree, we are trying to develop what is the characterizations of this or the gene bank of this bacteria. Now, this is basically a part of your what is called your biotechnology part, what is called your phenotypic and phylogenetic characterization has been made for this 65 degree temperature source that possess unique property. Now, if we have seen that optical density, just now I have already discussed that how we can measure this amount of bacteria present within a particular cell or a medium, right? What we have, it is a standardized curves we have prepared that if you have measured the optical density of 0.4, you can certainly call that it's around say 10 to the power in this range. Say, depending upon this, we can say that if we have measured the optical density, we can say what is the amount of cell concentration. Accordingly, we can choose how much quantity of bacterial cell is to be added to the concrete mix as a liquid forms. Then we have studied the morphological study of this bacterial stain at 65 degree temperature. This bacterium, as I already told you, is a long rod sepet, 5 to 10 micrometer long and 1 micrometer wide. This is a gram negative in nature. And we have also noticed that the growth kinetics, mostly we are getting at say 10 to 12 to 13 days. At this age, we are getting, that is the maximum density we are getting up to get. That means the growth is maximum at this range. Similarly, the pH, at a pH of in the range of 8 to 8.5, we are getting the maximum growth of this bacteria. And finally, the phylogenetic analysis of this bacterium has been done. And it is basically in this region, and we have named this bacteria as a BKH1, which is Thermoanorobacter species, has been determined. And this bacterium was affiliated with family with Firmicutes. It shares about 99.8 sequence similarity with the Thermoanorobacter thermohydrosulfuriceae. It is a facultative anaerobic bacteria. That means it is an anaerobic bacteria, but if oxygen is present, it will not die. That is what is called your facultative anaerobic bacteria. That is the advantage. In fact, other researchers mostly they use the Bacillus. It is aerobic bacteria. Now we have named this BKH1, and the gene accession number was FJ177512. We have also done with this microstructure analysis of BKH1 incorporated motor samples using this your scanning electron microscope and also the Qcrete analysis. And based on this, what we have got, that a new phase has been developed within this matrix, that is your calcium aluminum silicate phase, which is named as a gyelenite. And basically this bacteria leaches the silica and forms this gyelenite compound. Then comes to the part 3, that is what is called your Powder concept. That is, and for that we have got your US patent. Basically, what we have done is that we have isolate, purifications, and characterization of the protein, which is has some this enzymatic activity, that is which reaches the silica. We try to separate this protein. Now, isolation and purification of the protein is the basically bacteria. We know that the bacteria cells has many proteins, and this silica reaching protein is liberated by this BKH1 in the growth medium. So we isolate this protein from this growth medium by some techniques. The steps, if we want to make a short, that is the first we have to remove the bacteria cell from the growth medium, then concentrate the medium, removing the water. Then we purify the protein by double steps column chromatography. And if we see this, that the silica releasing activity of this protein, that is what is called your, this curve is your active protein, and this x-axis, that is what is called denatured protein. Denatured protein means if we can protein activity, that is the activity, silica releasing activity of that protein has been lost. How it is lost? Normally it is provided by heating. We can lose the activity of this protein. So we check it that if we add this active protein, it has a silica reaching capacity, but if we denature the protein, it has no silica releasing effect. Then we amount of protein, that is was measured by amount of silica releasing activity. Basically, this is very important. That is what is called your unique specific activity. That is how much milligram of silica is released per milligram of protein. Right. So because we are isolating the protein, now if we use 1 milligram of protein, how much microgram of silica is released? That is what is called your specific activity. In fact, at the optimum condition, it was calculated that 436 microgram of silica has been released per milligram of protein. Now, this is what is characterizations of this enzymatic activity of this protein. We are getting that this protein has in the same range around 8 pH. This has the highest silica releasing capacity. Now, also we have calculated the temperature, at which temperature this protein has given this maximum silica releasing. It is also giving it around 65-degree temperatures. Then salt tolerance activity of this protein, that is also we have tested, that is concentration of calcium ion if it increases, then what it says that this silica releasing activity is reduces. Initially it is more, then it is reduces. Similarly, the concentration of magnesium ion, that is the effect if we increases. So initially there is a decrease, and then it is there is no change in this silica releasing activity. So now we have studied what is the beneficial effect of this purified protein. and it is incorporated in cementitious material. As this quantity is very, very less, what we have done in these cases, it is small water bars has been prepared with addition of different concentrations. That is only in these cases we have used protein and the cement. The ratio of the protein and cement is given as 1:1 or 1:1.5:1. That is in the unit is milligram per gram. That is 1 milligram of protein has been added to the 1 gram of cement. That is the relationships. So we have also used the denatured protein by boiling for 10 minutes that I have already discussed. And after several days of water curing, we have tested. These bars are cutted in a small cubes, and then from this microbench device, we have tested this your compressive strain. And most of this study has been done in Netherlands. One of my colleagues, Professor B.D. Chattopadhyay, has gone there and they have done these tests. Now, what we are getting in that case is that this is what is your control, that is without any protein. Then there is active protein, and then there is a denatured protein. So what we have written in this case is that if we go on increasing the days of curing days, that if we added the active protein additions, give the improvement in strength compared to your what is called your control and also the denatured protein. And also if we see in this latter part that if we increase that protein concentrations, that is in this case 1:1, that is 1 microgram protein and 1 gram cement. In this case 1.4 microgram protein and 1 gram of cement, and 1.5 microgram protein and 1 gram of cement. This is the proportions, and we are getting the average strength increases. So if we increase the amount of protein, basically in this range we are getting high improvement in 47.5 to in this range. There is the improvement, and we are getting almost 23 to 26% with respect to the control. Now we have compressive strength study of the protein incorporated cement paste also we have done in the similar natures, and then we have studied this samples, that is control paste, then 0.2 microgram protein per cement, 1 microgram protein per cement, 1.8 microgram protein per cement. We are getting the similar results that if we increase your protein percentage, we are getting the strength is higher. So similarly in this case also, this is your protein treated and this is your denatured protein treated. So we are getting higher strength if we add protein into the cement based sample. Now, next, what we have done, some microstructure analysis of protein and incorporated cementitious material by environmental scanning electron microscopes. And what you have seen in this case is that this is what is called your unhydrated cement paste, and then there is a CASH gel. These are capillary pores, and this is your outer product, that is a low density CASH. Now, this is the EHM picture of cement paste samples at 28 days. This is for 1 microgram, and this is for your 1 microgram per gram of cement in different values. So somehow we can getting a more compact system in these cases. Now, what we are getting in these cases from this analysis of the matrix, that if we consider the CASH gel, that is at 28 days, that is what is getting, it is for the normal cement paste, and this is what is called your protein amended cement paste. We are getting the CASH gel quantity is higher in these cases, pore quantity is less, and unhydrated part is also in this case is less. So we are getting advantage in protein amended SAML, that we are getting less pore and less unhydrated cement. We have also done that nano indentator test to check whether the E value is changes or not. Then what we are getting, that average E value is 29 in these cases. If we add the protein, it comes increase to 34 GPa to 33 GPa in this range. And with respect to that, your standard deviations, that is your standard deviations values. So about 20% to 15%, there is improvement in your value of E values. Similarly, the average hardness is also increases 1.45. It is very hard. It is slightly less in these cases. So about 71 to 120% improvement has been noticed if we add protein in this case. So if we can improve this protein, basically we are E value can be increased, and there is a important parameters normally we needed at the present day to improve the E value of the concrete. Next, we have started with how this mortar can be, or this system can be improved to the crack repairs. So what we have done in these cases, we have done some artificial cracks on the concrete samples, cube samples, both in mortar cubes. We have some crack size is 5 centimeter length, 0.3 centimeter thickness, and 1.5 centimeter depth. In a prismatic mar, also we have crack size is 3.5 centimeter length, 0.3 centimeter thickness, and 1 centimeter depth. So these has been prepared by inserting, just like this is the top surface, we are inserting a plate, steel plate, and then after hardened concrete, that is, we just remove this plate. So that is the artificial, we can say the cracks has been developed both in your cube samples and your prismatic mortar samples. Now then it is filled up with your bacterial repairing. What we get in these cases, there is uncracked conditions. That is, if do not provide any cracks, then what is the flexural strength? It is 4.9 MPa, and compressive strength is 43 MPa. And if we do the normal repairing, that is after forming this, if we do the normal repairing, what we get is 3.1 MPa as a flexural strength, and 36 MPa is the compressive strength. So somehow we are getting less, although we have repaired it as the cracks has been poured and the crack has been repaired by normal mortar. Now we have the same cracks has been repaired with bacteria. Then what we are getting in these cases, this value has been slightly increased, that is 37, but it is not up to the uncracked condition. So we are getting percentage decrease with respect to this. In this case is 37 to 25. So there is an improvement in such sense, you can say. But if we come to this strength, compressive strength, initially it was a 43 when there was no crack. Cracked with a repair, normal repairing, it comes 36. It's quite less because of normal repairing has been done. But when it is repaired with bacterial concrete, we are getting almost 40, when that is almost similar to the normal strength. So we can, and on this basis of results, we have got a US patent on this for hot spring bacterial strain, BKH1 and protein isolated. They are from concrete composite and used there. Now, next come to the part 4. This is almost the concluding part. That is, it can be used as a self-healing systems. That is what is called your development of active and dormant stage. There are a lot of bacteria are present in the environment who are basically just like your forms an egg cell, right? And it becomes do not need any food, and they can survive for thousands or 1,000 years without any food and without anything else, because they are in dormant stage. Now, if the egg cell has been, say, slightly, but by any means it has been cracked or it has been broken, naturally then the bacteria becomes active. Then what is called your its actions will be start. So what is the advantage in this system, that if we can produce some what is called your spore forming bacteria, if we can add within the concrete, it will remain within the concrete for long years. But when by some means, if there is a micro cracks are developed, then what will happen? This these spores forming bacteria will get, this outer shell will get cracked, and then it becomes an active, and then it will start repairing these nano cracks. So in this way, it will called as a self-healing systems. Now we have also started these gene transformations, and we are trying to develop these spore forming bacteria. Basically, these are what is the system is called direct applications. You can do it is spore forming bacteria, which will remain within the concrete for a longer time. Now there are basically it is also terms of microencapsulation. There are two types of systems already existing nowadays. That if we can produce this microencapsulations, one system is your polymer plus catalyst. That is, if we can fill up these capsulations with some polymers and catalysts, and we can use within the concrete, but the size is very, very less. So that if there is some small micro cracks in develop, this outer shell become cracks, and this polymer and the catalyst will come out and fill the cracks immediately. So it will automatically fill these systems. Another is your biological route, that is, it can be filled up with some biological systems. That is, in that case, we have to think of some inactive or dormant bacteria, that is, they don't need any nutrient, but active when it is become cracked. So microencapsulations means basically the small capsule containing a liquid. It may be either polymer or a catalyst synthetic, or it may be some special bacteria which is remaining inactive or dormant state and become active when the outer cell become cracked. So it can be just like your vascular systems in our, it can be also look like this. That is, it's as a healing, can be treating as a healing agent. And one of the advantage of this, our system, biological system, compared to your what is called your chemical system, that it is more viscous and we can get a considerable strength recovery has been noted. Like our structures of the bone, basically we can know in our bones there is a tube inside diameter is there, and which is a very soft, and through this basically all the nutrient has been gone like this. So if we can make a systems like that, if in a concrete structures we can make this kind of vascular system, and which is filled up with some biological materials, then if there is any cracks is develops, it's automatically filled up. As this is less viscous, it can move very faster and it heal the cracks. So what is the novelty of this intention is that if we can, our intention is to heal the cracks at a very initial level, and also to improve the durability by using this bacteria. So naturally, if the structures becomes more durable, your carbon dioxide emission related to the cement productions will be less, and high cost of cement for affordable housing. Solution proposed by the invention is small amount of bacteria or the protein, both can increase the strength and therefore reduce the cement content. And also that what we have used in our studies, that this BKH1 reaches silica and forms the granulite crystal compared to the calcite formations proposed by the other researchers. And possibility of scale up of these inventions, protein can be added in dry conditions or with water during mixings. Protein should be prepared industrially. Microorganisms and protein is also compatible with Portland slag and Portland fly-ash based pozzolana cement also, that has been also studied. And some of the companies are already trying to push these materials. Already they have prepared some you can say the initial stage has been already over. So I hope in later part of we can get this kind of bacteria. Even this can be used in soil also, right? So if we add this bacteria in soil, that study has been not yet done. If we add this bacteria into the soils by spraying or by injecting or by grouting, it can improve your bearing capacity of the concrete. So lastly, I acknowledge for this funding, All India Council of Technical Education, Department of Biotechnology, DRDO, Government of India, and Intellectual Ventures Singapore, who have helped us a lot for this US patent. And acknowledgement from other researchers also, Dr. Guang and Professor Heng from Delft University, Professor S.P. Shah, Northwestern University, Professor V. Ramakrishnan, South Dakota School of Mines, Professor Yang Saki, Japan, Professor N.D. Valley, and also the current and past students. These are the all related publications. Thank you. Thank you for your patience for this lectures, and you can ask any questions, comments, or the feedbacks by mail or anything else. You can contact me. Thank you.
Good evening. Myself Latashri from Qcrete Readymix India. I will read out one question. Will bacteria spray on old structure increase the strength of concrete? It was asked by Mohammed.
That study is to be done. We have not yet done for any old structures. Basically, we've done for a normal during mixing, but we have to check it for the old structure. This is not study has been done.
Okay, thank you, sir.
Sir, thank you for a wonderful lecture. There are not many other questions. There is not much questions.
Sir, I have
Okay.
one more question. Is there, sir?
Yes, yes, yes,
Uh,
yes,
is
madam.
bacteria affected durability of concrete? It was asked by Akshay.
No, that bacteria is not affecting our durability. One of the reason is that in your hot spring bacteria, there is a lot of structures has been constructed in the outside, and these are not any much in your problems. And during our study, we have done some durability tests. At the time, I am not showing this result. That is your sulfate resistance test, chloride permeability test, RCPT test. These test results are there, but due to the shortage of time, I am not presenting all these details here. But it improved the durability. One of the reasons is that the pore structure has been improved, and the second reason is that your softivity test, there is improvement in softivity. So naturally, there will be improvement in durability.
Okay, thank you, sir. One more question. Will bacteria concrete good for earthquake resistant structure? It was asked by Dayakar.
You see, in this case, if we are increasing the E value only, let us think in that way, it can improve the E value of the concrete for the same grade, what we have checked, that in that way, it will take a less displacements, right? You see that for current practices that for a very high strength concrete, we are increasing the strength up to 100 MPa. But we cannot improve the E value in that proportions because it is square root of FCK. So if we can improve the E value in other methods, naturally we can get an advantage. So we are getting the strength. Suppose if we have a earthquake resistant structures, in that case, the main problem is the deflections, right? So if we can reduce the deflections by E value, increasing the E value, naturally we can get some advantages. Otherwise, there is no such advantage in earthquake resistant structures. Only
Okay,
if it
thank you,
can
sir.
improve the E value.
Okay, thank you, sir. One more question. Is it possible to incorporate bacteria in geopolymer concrete also? It was asked
We
by
have not yet
Anup
tried.
KN.
We have not yet tried. Naturally, it is possible. You can do that. Lots of work is also going on for bacillus bacteria, using bacillus, but our bacteria is not yet started because it is our own bacteria. No, you cannot get from any lab or something else.
Okay,
Okay.
thank you, sir. One more last question. Is there any effect on reinforcement when used in RCC? It was asked by Harsh Raj.
We have not yet studied, but you see, the system is to be studied. And so far, my concern is that as there is no change in the pH value or your total bonding or something like that in your strength, naturally it will not affect the reinforcement this bacteria. Even there are some studies has been also going on that you can use as a coating for the reinforcement using this bacteria. Just a positive effect. Okay.
Oh, okay, sir. Thank you, sir. Now I'll hand over this session to Engineer Shaiju Nair, sir, for vote of thanks.
Yeah, good evening all. It was Dr. Saroj Mandal sir. It was a very, very excellent topic. Even now, whenever we are listening the word bacteria, fear factor is coming in the mind first because it will create some harmful atmosphere like that. So let me come to my responsibility. So first of all, I would like to thank our speaker of the day, Dr. Saroj Mandal sir, for delivering an excellent speech on bacterial concrete. He touched upon the factors starting from selection, compatibility, and design, applications, and even the benefits of using such innovative material. A special thanks to our ICA chairman, Dr. Anil Joseph sir, and our ICA Secretary, Kochi Chapter Secretary, Dr. Job Thomas, and all other ICA executive members for organizing such a wonderful program. Also, a special thanks to Qcrete Readymix India Private Limited, Engineer Shelly Fernandez sir, Engineer Kaushika, and all other office bearers for organizing such wonderful webinar series in association with ICA Kochi chapter. Our heartfelt thanks to the participants who are actually gathered in huge numbers, which is giving motivation for us to organize such webinar series, more and more webinar series. So once again, thank you all. Hope you all enjoyed this session. Thank you. Good night. Thank you, sir.
Thank you.
Yeah, I think we can.
Thank you.
Now. Yeah, please.
Thank you, Saraj
Thank you
Mandal,
all.
sir.
Thank you.
Thank you.
Thank you,
Thanks
sir.
for the
Thank you very
audience.
much
There are
for the excellent presentation.
there are
Thanks a lot.
some more questions. We'll send it to Dr. Saraj Mandal, sir, and get the feedback. Yes, sir.
Okay.
A lot of other questions are there. We'll get back. We'll answer. Means we'll get the answers from you and send it to the people who have asked. Thank you. Thank you. Thanks a lot.
Thanks. I'm leaving now. Huh?
Yeah. Thank you.